Hello everyone, welcome back to Math with Allison. Today we are beginning a new series, woot woot. So we're going to be talking about parametric and polar curves. So we are just starting with an introduction of parametric equations. So let's go ahead and dive into it. What are we used to working with? We are used to working with functions. Y is equal to f of x. We have some input x and we end up with an output f of x. So here's something like so here we have a little example of that. When we have y equals f of x, we have two variables. We have x and we have y. What if I wanted to add another variable? What would this variable be? Well, a very common real life variable that we use is time. What if I want to know the position at a specific time? So let's go ahead and see an example of that. We have a boat travels in this circular course. We can see he's really happy on his boat. It is a circle. They start at the point 40 and they're going around at a radius of 4 miles. And they complete one lap every 2 pi hours. And it has a constant speed. So we have this little guy on a boat. He's just trotting along. What do we know? It normally is the equation of the circle. We know that x squared plus y squared is equal to the radius squared. So that's going to be 16. But this isn't telling me his position at a specific time. This is telling me his position x, which is going to be his x position, and his position y. But I don't know at what point in time where he's going to be. I want to know if time is equal to 3 pi over 2, where is he going to be? So let's go ahead and rewrite our equations in terms of time. So when we're working with circular functions, we have that x is equal to r cosine theta, and we have y is equal to r sine of theta. And remember, theta represents the angle. But remember, we want to work with time. So we're going to have that our angle is going to be represented by time. So we have x is equal to r cosine of t, and y is equal to r sine of t. So now we can plug in the radius. And now we can describe the position in terms of time. So it's going to be x of t, and it's going to be y of t, for t values greater than or equal to 0. So its position is going to be 4 cosine of t, 4 sine of t. So now it's not a function y depending on x, x depending on y. Both x and y are going to depend on the time. So now I can find his position anywhere at any time. So what are these called? These are called parametric equations because they rely on a parameter. For us, t is going to be our parameter. So for example, when t is equal to 0, we get 4 cosine of 0, and we get 4 sine of 0. Well, we know that cosine of 0 is equal to 1, so we get 4, and sine of 0 is equal to 0, so we get 0. And that is indeed the starting position of our little guy on the boat, right? So now let's go ahead and try some other examples of this. We want to graph and analyze the parametric equations. So we have x of t, which is sometimes written as a function of t, so f of t is equal to 2t. Y of t, which you could also see as g of t, is equal to 1/2 t squared minus 4. And this is going to be for time between 0 and 8. That could be minutes, that could be hours, whatever you want to interpret it as. So in order to graph this, what we have to do is plug in our time values and see the outputs. We can see our x value and we can see our y value. So what I like to do is I like to work it out with a chart. So f of t is equal to 2 times t. So if we plug in t equal to 0, we get 0, 2, 4, 6, 8, 10, 12, 14, and 16. I just multiply all of those by 2. Then we get 1/2 t squared minus 4. So when we plug in 0, we get negative 4. Let's plug in t equal to 1. We get 1/2 times 1 minus 4. So 1/2 minus 4, you can just think of that as negative 3.5. Now we can plug in 2, so 1/2 times 2 squared is 4. We end up with 2 minus 4, which is equal to negative 2. 1/2 times 3 squared is 9. So 1/2 of 9 is 4.5. 4.5 minus 4 is equal to 0.5. Let's plug in 4. We get 1/2 of 16 minus 4. That's 8 minus 4, which is equal to 4. 1/2 of 25 minus 4. That's 12.5 minus 4, so we get 8.5. 1/2 of 36 minus 4. 18 minus 4 is equal to 14. We're almost there. 1/2 of 49 minus 4. Half of 49 is 24.5. 24.5 minus 4 is equal to just 20.5. And then 1/2 of 64 minus 4, 32 minus 4 is indeed equal to 28. So let's go ahead and try to graph these out. So when t is equal to 0, my f of t, you can think of that as an x, right, is equal to 0. But our y of t, our g of t, is equal to -4. So I'm going to go over 0, down -4. Then I'm going to hop over to t equals 1. So my f of t is equal to 2. And I'm going to go down -3.5, which is going to be somewhere like here. Then I go over to 4. I'm going to go down -2. When I'm at 6, I'm going to go up to 0.5, so it's barely above. Then I'm going to go up to 4, right? I'm just increasing my x by 2 each time, and then I'm just adjusting, my g of t accordingly. After 4, we're going to go up to 8.5. Then we're going to go up to 14 itself, 20.5, and 28. So we're going to go all the way up to 28. So my 16 is off right here, huh? My 16 is supposed to be right here, but that's okay. So what does this look like? It looks like a little curve that does something like this. Something else we also have to indicate is the orientation. Which direction are we going in? Well, when time is equal to 0, we're moving in this direction. So that's how you can indicate the orientation, is you can add those little arrows. It describes the direction of the parametric curve in terms of time, because sometimes it could be going this way or it could be going this way. It's important to know. So let's go ahead and see an example of that. Here we have x of t is -2 plus 6. Y of t is 3t minus 5, and we have t values between -5 and +5. So let's go ahead and plug in some t values. When I plug in -5, I'm going to end up with 5 plus 6, which is 11. 3 plus 6 is equal to 9. 1 plus 6 is 7, and then we get 6, and now we get 5. -3 plus 6 is 3. -5 plus 6 is indeed equal to 1. So notice now our x is going to be moving in that opposite direction. Now let's go on and find our y of t's. So 3 times -5 is -15, minus 3 is -18. Then we get -9 minus 3 is -12. -3 minus 3 is -6. 0 minus 3 is -3. Now we get 3 minus 3, 0. 9 minus 3 is 6. And 15 minus 3 is equal to 12. So now let's go ahead and fill in our graph accordingly. So first we're going to start at x of t is equal to 11. So we have our 11 right here, and we're going to go all the way down to -18. Now we're going to go over to x, which is equal to 9, and we're going to go down to -12. Then we'll go to x is equal to 7. We're going to go down to -6. X is equal to 6, we get -3. And then x is equal to 5, we go up to 0. Now we're going to go to 3, and we're going to go up 6, and we're going to go to 1, and we're going to go up 12. So we can see this is actually just a wonderful straight line. Now this is where the orientation matters, because just by looking at this, you might think it goes down to the right, but it actually doesn't. We have to indicate the orientation because it's going to go in the opposite direction of what we think. So that's all I have for us today in this video. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.